Hello all, this is VLSI updates. Hope you all are doing well. In this session, we are going to see a basic digital design. You can say it's an interview question which is frequently asked about multiplexer. So we all are aware of multiplexer, and here we are going to see how to multiplexers are being used in variety of applications, not just logic gates implementations and all. So in this section, we are going to see a little bit details about how we can implement logic gates using multiplexers and all. Let's get started with that. Um, why multiplexers are used to implement logic gates in ASIC and FPGA? We can use multiplexers to implement logic gates. Okay, so we will see the reasons why it is important and how we can implement the different logic gates using 2 to 1 multiplexer here. So multiplexers are often used to implement logic gates in ASIC and FPGA because of that versatility and efficient and can be easily configured to perform a wide range of logic functions. Uh, it's mainly due to its flexibility and the efficiency and the performance and the ease of implementation. We choose to go with the multiplexer to implement logic gates. This is the frequently asked interview questions: how to implement OR gate, AND gate, NAND gate, NOR gate, XOR, XNOR gate using multiplexers. So let's see one by one how we can implement these gates using the 2 to 1 multiplexer. And let's see the AND gate first of all. So we all know the AND gate and the corresponding truth table here, and we have the 2 to 1 multiplexer implementation here. uh, so in this configuration, if it's the truth table, for the AND truth table, when both the inputs are high, the output is high. Okay, so for the multiplexers we need select input and two data input, one output. For the AND gate we need only two inputs and one output here. So in this case, I am taking the first data input as a select input to the multiplexer here, and I am connecting the same data input to the select input to the data input of multiplexer here. Right. So on the other input, I'm connected to the data input one of multiplexer here. So this is the basic configuration. So in this case, if you see, so when A is zero, when A is zero, the output is always zero. So we are just connecting the same select input to the data input here, and that will become the output of Y. So when there is a zero of A, the output will always be zero here. So when there is a one, when the select input is one, so the output follows the B here. So if you see here, this is the output 0 and 1, and this is the B input 0 and 1. So I'm connecting the B input directly to the data input 1 of multiplexer, and that will be the output here. This is the basic way of implementation. Just remember the truth table here, and just take this one input of the AND gate to the select input of the multiplexer, and based on the output here we can just connect the 0 to this place, and uh, B input to this data input 1 here. So this will help us realize the AND gate functionality here. So you can directly write the logic for AND gate here instead of going for the AND gate. Practically, the idea is like implementing using multiplexer is faster than the AND gate here, as the data path provides a lot of flexibility here. So that is the reason, and also the space efficiency and the resources availability, right? So we can utilize the resources by implementing the logic gates functionality using the multiplexer, and that's another advantage. And this is for the AND gate. Let's move for the OR gate. So for the OR gate, when there is any of the input is high, the output is high. So in this case, I am connecting the one of the input to the select input here. So when A is 0, the output follows the input. So the output follows the input B. And when A is high, the output is always high. I am connecting output to the 1 here, constant 1 here. Okay, this is a simple way of implementing. So have one select input here, and just compare the select input. Select input is 0, the output follows the input here. If the select input is 1, the output is always high here. So this is simply way of implementation for the OR gate. Similarly, we can go for the NOT gate here. For the NOT gate, it's an inversion function, right? So when the output input is 0, the output is 1. When the input is 1, the output is 0 here. And in this case, so my x is my select input here. When x is 0, I will connect it to 1. When x is 1, I will connect the input to 0 here. So this is the simple implementation of NOT gate using 2 to 1 multiplexer here. And the remaining gates, NAND gate. NAND gate is inversion functionality of AND gate. So you will see when both inputs are high, the output is 0. So in this case, I think I missed the bubble here. Just assume it's a NAND gate, okay? And I'm connecting the input to the select input of the 2 to 1 multiplexer here. So whenever the input is 0, the output is always high. The output is always high. And when the select input is 1, the output is inversion of the B input. That's why I mentioned the B bar. Here we need one AND gate to invert the B input and connect it to the data input 1 of the multiplexer. We need one AND gate here additionally. Okay, so this is for NAND gate. Let's move for NOR gate. NOR gate is inversion of OR gate. So when any of the input is high, the output is going to be 0. When both inputs are 0, the output is high. So let's connect the same input to the select input here. And when the select input is 0, the output is inversion of the B input. So inversion of the B input here. And when the select input is high, the output is constant 0. The output is connected to constant 0 here. And similarly for the remaining gates, for the XOR and the XNOR gates here. For XOR gate, we know that when any of the input is high, and the output will be 1. Okay, when both inputs are same, the output is 0 always here. So in this case, I'm connecting my A input to the select input here. So if my select input is 0, and my output will follows the input. So I'm connecting the B to the output here directly. Right. So when my select input is 1, my output is inversion of B input. 0 1, it's 1 0. So here I'm just connecting the inversion of the B input here. So this will realize the XOR gate functionality here. And similarly we have for the XNOR gate. And in the XNOR gate we have the A input. When both inputs are same, the output is high, right? When there is a change in the input, the output is 0 always here. So I'm connecting this input to the select input, and when the select input is 0, the output is the inversion of the B input. So B input is inversion here, and when the select input is high, the output is just a B input here. So these are the basic implementation using the multiplexer. Similarly, you can implement any complex circuits like adders, half order, full order circuits, and comparator circuits. So any complex circuits also can be implemented using multiplexer. Multiplexer is a very important circuit in digital design. And let us practice with multiplexer. What are the different circuits can be implemented, because this is widely available resources. So when there is a resources crunches over there, it will save a lot of space for the implementation purpose. And also it's always look into the alternative and the better performance implementation as a design engineer. Okay, so just practice these things, and this is the basic interview questions, and this can be used for both the ASIC and FPGA, and we will come back with the more informations on this, and let's stay connected on this. Thanks for your time. Yeah.